Hello, and thank you for taking the time to come to my talk today. My name is Boel Nelson, and this talk is titled Efficient Error Prediction for Differentially Private Algorithms. As you may have guessed, this talk will be about differential privacy. I will also explain why error prediction is important in this context and how we can predict error efficiently. So, what is differential privacy and why should you care? First off, differential privacy is a definition that dates back to 2006. Basically, differential privacy describes a statistical relationship. Now, what does that exactly mean? I will get back to you with the exact definition, but essentially it means we're able to give formal privacy guarantees that we capture with a variable called epsilon. So if you heard about differential privacy, you might have also heard about epsilon. And if you haven't, don't worry. I'll introduce all the relevant terminology right now. Imagine that we have some sort of function f. This could be an algorithm or a database query. For example, f could contain a query like this. Select salary from some table, and then we calculate the sum on this data. So let's assume f is this very simple query. Then we also need some data to do our calculation on. So let's assume we have two databases. We'll call them D and D prime. Now, what's important is that these databases, D and D prime, are almost the same. So what do I mean with almost the same? We need to define that. I'll show an example where the database to the left has 3 records, containing the salary of Alice, Bob, and Boel. And then, the database to the right contains the salary of just Alice and Bob. So, these databases differ on exactly 1 row. Therefore, they are almost the same, and we say that D and D prime are neighboring databases. As we can see from this example, we can create D prime from D by removing just Bob's row. So when I say the databases are almost the same, I mean the databases are neighboring. Now, going back to our query f again, let's run f, the same f, on both of the databases, and then we want the result of the query f with high probability to be almost the same for both runs of the same query. So basically, the results should be indistinguishable from each other. This way, we will be able to hide whether Bob was in the database or not. Since the outputs are almost the same for the database D with Bob and the database D prime without Bob. Essentially, we can hide the absence or presence of Bob or any other person for that matter. To exemplify, let's look at the content of the databases I showed earlier again. Now, if we run our sum query f on the left database, we get 6 units. And if we also run our query f on the right database, we get 4 units. How can we make these results appear similar or indistinguishable, if you will? Basically, how can we define this notion of almost the same? In other words, how close should the results be? This is where the definition of differential privacy comes in. Here, the question of how close is answered by epsilon, the variable that I mentioned earlier. So what epsilon does is that it bounds the distance between the results. If we formalize it, we can define this as the probability of running query f on the database D and getting results R differs by a small term e to the epsilon and is less or equal to the probability of running that same query f on the database D prime and still getting the results R. So here that term almost the same is captured by this e to the epsilon. Now, if this formal relationship holds, we will be able to say that an algorithm, f in this case, is epsilon differentially private. So, to summarize differential privacy, First, differential privacy is a definition, not a specific technique. And differential privacy is a property of the algorithm, not a property of specific data. And lastly, differential privacy offers quantifiable privacy guarantees, which means we can express privacy, or actually privacy loss, as epsilon. Sounds great, right? But how do we usually achieve differential privacy? You probably guessed it already. The answer is we usually inject controlled noise. That means in order to achieve privacy, we need to introduce inaccuracy. Basically, we pay for privacy by adding an error to our results. In this talk, I will use the terms inaccuracy and error interchangeably, as accuracy is the lack of error. Then, if we actually want to use differential privacy in a real application, we are also likely interested in accuracy, being sufficiently high for our application. So, how can we express the accuracy of an algorithm? In the literature, accuracy of differentially private algorithms can be expressed through Chernoff bounds. This is an analytical expression of error. And what these Chernoff bounds do are that they are able to bound the error to be smaller than a variable alpha with high probability. Returning to our example with our sum query f, we could find the Chernoff bound to tell us how big our error is. Perhaps we would get something like this. The error is plus minus 3.58 units. This is really useful if we want to be able to reason about accuracy before deploying our application. Still, to be able to use these Chernoff bounds, we need to know the relationship between our query f and the result. And what if we don't? Then we can't use the Chernoff bound. Instead, in this paper, I propose applying a statistical method to empirically predict error. Let's again use an example to motivate the need for an efficient method here. Imagine that you want to bake a cookie, and you want to make the best cookie. Now let's assume you already know the best recipe for a cookie, and that you have a metric for measuring how good your cookie is. Still, you need to figure out what temperature should you set your oven to, and how long should you put the cookie in the oven. These two variables, temperature and the time, are obviously connected. Your cookie will get burnt faster if the temperature is higher. But how exactly are these two connected? Naively, one can measure the taste of the cookie at all possible combinations of temperature and time, but that wouldn't be very efficient. Therefore, we adopt a statistical method called factor experiments, which will tell us how to select the points in our space where we should measure in such a way that we can run the fewest experiments. Back to the cookies. With the naive approach, we want to construct all combinations of time and temperature, and then measure the tastes for each of these settings. Then we can also reduce the amount of combinations by removing some settings that are obviously illegal, in the sense that it might be physically impossible for the cookie to bake at a too low temperature, for example. So we'll be able to reduce our space to only include relevant combinations. So we might end up with temperatures in the range of 100 to 250 degrees Celsius and time in the range from 4 minutes to 30 minutes. Then, with a step of 10 degrees and 1 minute respectively, this gives us 15 times 26 combinations, which results in 390 experiments that we need to run. In comparison, factor experiments would tell us that the most important settings to measure are the edges of the space. That is, we would measure high temperature with long time, high temperature with short time, then low temperature with long time, and low temperature with short time. So we can reduce the experiments we need to run from 390 to just 4. Then we use this data to create a linear model to predict the score of any cookie within the given space. So how does this scale, you wonder? Since we measure a high and a low setting for each variable, a system with k variables would mean we need to run 2 to the power of k experiments. Now we have a method to efficiently use empirical measurements to find the relationship between the input variables and the result. Hence, if we have a differentially private algorithm with some input variables, and we can view the database as one of those inputs, we can measure the noisy result, compare it with a true result, and describe the error as a linear function. In this paper, I've chosen a differentially private algorithm where the error is particularly difficult to predict since there are 6 input variables. By using factor experiments, I was able to create a prediction model which describes how each variable contributes to the error, and as we can see, there are also variables that interact, and those are also described by the model. So, how did I do this? First, identify the variables in your algorithm. If you end up with many variables, it is possible to systematically run a smaller version of your experiment to discover if there are variables that can be excluded. Then, since error in differential privacy is probabilistic, measure each setting multiple times to get the average error. Then, run your experiments and create your linear model. This is easily done. In fact, it is one line of code in the language R. Next, validate your model, and if your model checks out, you're good to go. Otherwise, you can reduce the space you create your model for systematically, or you might have forgotten to include an important variable, and it can also be the case that your system is in fact non-linear, and then you need to add some more combinations to your experiment. But once your model checks out for your validation, you can now plug in any values from your space into your model. This means you can predict your error for a given setting. For example, our cookie score model from before will be able to predict the score of a cookie baked at 180 degrees for 16 minutes. You can also use your model to find solutions where error is minimal. For example, if we want a cookie with a perfect score, our model might tell us that this happens at 210 degrees for 11 minutes. We can also use the model to find in what range our cookies score as fantastic. So basically, a prediction model can help us tune our variables before running our differentially private algorithm. So, in conclusion, I am able to show that factor experiments can be used to predict error for differentially private algorithms. This methodology is particularly interesting since it allows us to model how and if data affects error, which purely analytical models often omit. Also, if your algorithm has other input variables, our model will be able to capture their possible effect on error too. The selling point here is, of course, that conducting factor experiments is more efficient than varying one single variable at a time. As for future work, it would be interesting to examine how well this method works for other differentially private algorithms. For example, can we predict error for the differentially private algorithms offered by well-known libraries such as IBM's diffprivilib, McSherry's Pink, or Google's TensorFlow privacy? Also, it could be beneficial to create a tool that automates my proposed methodology to make sure error prediction becomes more accessible to the entire community.